Hi everyone, I'm Amy. I'm the Motus coordinator for British Columbia with Birds Canada. Thanks for having me here to talk about working with Motus data. I wish I could be with you in person since it sounds like a great week of learning about building Motus stations and tagging birds. However, I'm hopefully on the line to answer questions. I'm joining you from Vancouver, British Columbia, and I'd like to acknowledge that the land on which I live and work is within the traditional and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh First Nations. I acknowledge the deep connections to and the history of these communities on this land, and I'm grateful for their continued stewardship here. Today, I'm aiming to give you an introduction into how to access Motus data and then process it so you're ready to start analyzing it. Every analysis is unique and depends on your research questions, so I want to focus on the steps that lead up to your analysis, getting the raw data from the Motus database into shape for your analysis. I like to think of this process in 4 steps: downloading the data using the Motus R package, understanding and manipulating the structure of Motus data, then cleaning Motus detection data, and finally mapping and analyzing your data. Working with Motus data can be challenging, and there's definitely a learning curve, especially if you're new to coding in R. I'm going to cover a fair bit of ground in this session and go through a lot of code. So this presentation and all the associated R code are available for you to download and revisit anytime at the Google Drive link here. And you may also find helpful material on the Motus GitHub page, which is linked, and the Motus R package website, which is down in the bottom left corner there, which has several detailed articles on working with Motus data that you may find helpful as well. So I encourage you to revisit any of these materials anytime, and hopefully having them provided will be helpful when you go back to revisit and Motus data and work with your own data. So before we get deep into the data, I thought I'd show you how the various components of Motus are linked. So here's a basic overview of how Motus works. Essentially, you have researchers or collaborators who are deploying radio transmitters on animals, which are then detected by the receiver stations when the tagged animals are nearby. And the key that makes Motus work is that these tagged animals are able to be detected on all the receivers in the system. So researchers can capture large, even hemispheric scale movements, as well as local and regional movements. So this relies on all the detection data that are collected by Motus stations being housed in a centralized database. And extremely importantly, that researchers submit metadata on the species tagged and the stations deployed to this central database. This is what allows tag detections to be linked with the animal carrying the tag. And then summarized data is available on the Motus website. But when researchers want to analyze tracking data collected through Motus, they can use the Motus R package. And we're going to focus on using the Motus R package and working with your data in R today. So on the Motus website, the data you can view is summarized, and it has already been filtered to remove any false positive detections. Due to the nature of radio telemetry technology, Motus can be susceptible to false positive detections that could result from anthropogenic noise in the environment, mimicking a tag signal. So when you download your data through R, though, you get all of it. The raw detection hits down to the second, and the data that has not yet been filtered as it would have been, as you might see on the summarized data on the website. So fortunately, we can inspect the raw complete data to remove those false positives. But first, however, let's take a look at some of the basic units of Motus detection data. So the key that makes Motus work, as I mentioned before, is that the tags operate on a shared frequency, thus enabling shared receiver infrastructure across large areas. So this means we need another way of uniquely identifying the tags than having them operate at different frequencies. So first, tags emit bursts. These bursts equal one transmitted signal from the tag. And these bursts contain 4 pulses within them. And the intervals elapsed between those 4 pulses in milliseconds is how the tag ID is encoded. This is measured to a high level of precision, and these are termed hits. So you get 1 hit of your tag on a Motus receiver station, and that's what they're called in the Motus database. So you have a unique numeric hit ID for each burst or hit of a tag on a receiver. And second, there's the time elapsed between these successive bursts or hits emitted by the tag. And this is what we call the burst interval. So the tag ID is contained within the burst, and then the burst interval is the time elapsed between 2 successive bursts. And combined with the tag ID encoded in the burst, this gives us our unique identification for each tag and therefore each tagged animal. Therefore, to identify a tag, we need at least 2 bursts because we need to measure the interval between them. 2 or more consecutive bursts or hits, they're kind of equivalent terms, equals a run. And each run also receives a unique numeric ID in the Motus database. So each run ID contains 2 or more hit IDs. So those are our basic detection data units that we're working with: hit IDs, run IDs. So now I'll briefly introduce how Motus data is stored. These tag signals are detected out in the environment by Motus receiver stations, and then that data comes back to Motus either by being transferred over Wi-Fi internet, over the cell network, or it's manually downloaded from the receivers and then manually uploaded to the Motus website by researchers. Once that raw radio data gets to Motus, the tag finder algorithm processes the data and identifies the Motus tag detections within the data, which are then stored in the centralized Motus database. Tag and receiver metadata is entered into the Motus database by researchers, and it's of utmost importance that folks enter their metadata correctly and keep it up to date, because metadata is what allows us to determine which animals were detected and where. Without metadata, we only know that a particular tag was detected. We have no way to know what species it was on, or where the tag was deployed on an animal, or where it was detected. So the Motus database brings these together: the metadata submitted by researchers and the raw radio data coming in from the receiver stations. The Motus R package is what allows us to download our Motus data from the centralized Motus database. When we download Motus data, it's stored as an SQLite database, which is composed of several interrelated tables. So it's a relational database. This is much more efficient and saves computer memory compared to storing the data in a big spreadsheet, since you can easily get a lot of data with Motus, millions of lines, if you have a big project. So once you download your data in an SQLite database, you'll have a number of tables, such as tag depths, which is your tag deployment metadata, hits, which is the detection data at the individual hit level, activity, which tells us about radio activity within each hour, runs, which is the detection data associated with individual runs, and then receiver deployments, which gives you the metadata for your receiver deployments. And then information from these various tables are compiled into a view called all tags that contains all the data most people will need to work with their Motus data. So that's often what you'll be working with when you analyze your Motus data, is the information brought in from these various related tables into this all tags view. So once we get into the code, I'll get into this in more detail. Mainly right now, I wanted to highlight how Motus data downloaded using the R package is stored as a relational database. And you can find out more about each of these tables on the Motus R package website, which the articles are linked on the slide there. And just a note, as always, please ensure your metadata is kept up to date, because that's what allows us to get accurate data from Motus. All right, so now that we've got a brief introduction to the structure of Motus data, it's time to get started. So we use the R programming language to work with Motus data, and I've included a link to where to download R in case you haven't installed it before. You can work in base R, but it's much easier to use R through RStudio, which is basically an interface for working in R that offers you a lot more functionality and ease for running R code. So the link to download RStudio is there as well. And the Motus R package website has instructions on how you can install the Motus R package, which allows you to download your Motus data through R. So I want to walk you through the workflow that I use when working with Motus data. There are many ways to do this. So this is just my personal preference and how I like to keep my work organized and what works for me. You may find different methods make more sense to you, but hopefully this is a helpful base to begin from. If you're new to R, I'd recommend the online book R for Data Science. It offers a great introduction on how to work with data in R and best practices, and we'll put a lot of those practices to use while working with Motus data. So the first thing that I highly recommend is creating an R project for the analysis that you want to do. I didn't know about R projects when I first started using R to analyze data, and once I found out about them and started using them, they improved my organization a million times over. So essentially with an R project, you'll have a folder created for that project on your computer, and then that folder will be your working directory while working on that project in R. That means if you save a file to your computer from R, that's where it will go. If you load a file into R from your computer, that's where R will look for the file in your working directory, which is the folder for this project. Within that project folder, I create subfolders for the different parts of the project, for analysis, which is where I store my saved R code scripts, figures, which is where I store any plots that I make, and then any other kind of places I might want to store data that I want to export out of R so that I can look at it or just make sure I have a copy saved so I don't have to recreate it every time. This all keeps me organized, and I know where to find things when I return to a project after months away from it. So definitely recommend using an R project to keep your analysis organized. Okay, so let's jump into R itself. So I'm going to bring that up on the screen here. And so here is my R environment using RStudio as my interface. And you can see up in the top right corner here, this is my R project. I've called it Example Motus Workflow. And then if I open up my file directory, you can see here, depends, you can save it wherever you want on your computer. I have a whole bunch of different R projects, but you can see that I've got a folder called Example Motus Workflow. So that's where all of my files associated with this project are stored. All right, so back to RStudio. Up here in the left, I've got my R script that's got all the code we're going to run today to download and process Motus data. And then in the other panes, we'll see some output coming here in the bottom left corner. We can see our file directory in the bottom right. And right now we haven't loaded anything into R yet or created any tables or anything, so it's empty. But this top right pane will show us what we have in our session once we get going. All right, so first step is we want to download the data from the Motus database. And so this R script, I've included a whole bunch of notes in it, and you can work on it, go back and read it yourself as well. You feel free to take the copy from the Google Drive and modify it to suit your purposes or anything. It's there to help you work through downloading your Motus data. So it's got a few steps of what we're going to cover. First, we'll download the SQLite Motus database for the tags that we're interested in. For this workshop, I'm going to use some data from the project, one of the projects I work on, which is a project tracking Dunlin in the Fraser River Estuary here in BC. And then we'll load that detection data, pull out some specific tags that I want to show you, and then we'll do a basic filter on that detection data and make some maps and other diagnostic plots so we can take a look at what's going on, assess whether there are any false positives we need to remove from the data, clean that data, and then save a copy of our cleaned and processed data set that's ready to be analyzed. All right, so first up, I have some code here that shows you how to install the Motus R package if you haven't already done so. It also has some code for installing the other R packages that we're going to use to work with our data. So I'm not going to run that right now since I already have the Motus R package installed on my computer, but if you need it, the code is there to do so. Okay, so next we're going to do just some setup to get everything ready to start working with Motus data. So first, we have to load the different packages that we're going to use to work with the data. There are quite a few of them, and I've just got some notes here about why we need them, what they're going to be used for. So the first one is evidently the Motus package, which is what's going to allow us to download our data. So I just run each of those lines of code to load those those R packages. And you can see in the bottom here, they're connecting, they're loading, so that's good. And then what we want to do is set our time zone to UTC or Greenwich Meridian time. And so that's to make sure that all our times are consistent, so we don't have some data in one time zone and some data in another time zone, which could mess up our analysis. So we want them all to be in the same one. So this line lets us set our time zone. And then I also have another script of our code that has some useful functions that we'll use later on. And those functions are just snippets of code that do a certain task that we want. So in order to load those functions, we just source that R script, which is also saved in the same directory. And I have it up here on in RStudio as well, just so you can see it. But essentially, we're just going to source those functions so we can use them later. And you can see here, now we have several different functions that have been loaded in that we can use later on to work with our data. So this one, for example, adds a deployment location for the tag, that kind of thing. All right, so we have a little more setup to do. We are eventually going to make some maps with our detection data. So first, we're just going to load some shape files for the world. And then we're going to load a few more shape files that'll just give us a little bit nicer looking maps. And these come from the R Natural Earth package, which we loaded previously. So those will just provide us with some base maps once we get to the mapping stage. All right, so now we've got everything set up to start our work with Motus data. That's all the kind of basic background you need to set up your workflow. So now it's time to download the SQLite databases for the project. So you only need to do this when you're first downloading the database from Motus if you've never downloaded data from that project before, or if you're updating your data because you think new detections have come in since you last downloaded it. If that's not the case, you don't necessarily need to download or update the data every time. And you'll save quite a bit of time that way because downloading the data, especially if there's a lot of it, can take quite a while. So downloading the data saves this SQLite database to your computer. And in this case, it's going to save it to your project folder. And I've set it up to save in a subfolder of that project folder called SQL databases. So we can look at that here. I'm in my project folder. There's the subfolder SQL databases, and within it we have a couple projects here. The one we'll be working with today is project 349, which is the Fraser Estuary Dunlin project. And you can see it's a .motus file, which is that SQLite database. Okay, so this code here with the tag me command downloads your Motus data. You specify which project number or which receiver ID. You can download by either project or by receiver. If you download by project, you get all the detections associated with the tags within that project. If you download by receiver, you get all the detections of any tags that have been picked up on that particular receiver, but not on any other receivers they've been picked up on. If you're downloading for the first time, you want to say new is true because you're downloading a new file. If you've downloaded before and you're updating, you can set new to false, but update to true. This force meta makes your metadata update in case corrections have been entered or new metadata has been entered. I usually specify that to be true just to make sure. And then we have the directory where we want the file to be saved on our computer. It'll also prompt you to enter your Motus username and password. So I'm not going to run that right now because it takes quite a bit of time to download these data, but I will show you what you should see. Basically, when you run that command, you'll be prompted to enter a login name, which is the same one you use on the Motus website, and a password, which is the same one you use on the Motus website. For an example project, I've put in motus.sample and motus.sample, but it'll be your Motus username and password for your own data. And then you should see a message that it's checking for new data, and then once it's got some, it'll start downloading new runs and hits. All right, back to R. Okay, so once you've downloaded your Motus data, it's saved on your computer. Then we want to load that data into R. So we need to connect with that SQLite database. So what we can do here is specify where that SQLite database is loaded. We saved it in that SQL databases subfolder. So we'll enter that, and then we can connect to that in R. So I'm creating an object named SQLDB, SQL database, and then using that same tag me, but you'll notice I've changed new to false and update to false because I don't want to download any new data. I've already downloaded before, so we're good to go. And that shows up here in our environment. We now have an object called SQLDB. All right, so within that object are all those interrelated tables. So first, let's look at the species table. So this project is tracking shorebirds in the Fraser Estuary, mainly Dunlin. So we're going to look for Dunlin only. All right, so let's check the species code to make sure we are calling the correct species when we go to load this data. Okay, so now we have a table called species, and we can click on that to open it up. And well, what we see, we've got Dunlin, semi-palmated sandpiper, and house sparrow. So I'm suspecting those house sparrows are associated with some false data, and for false positives, we don't necessarily want to load that data. I'm not interested in house sparrow or semi-palmated sandpiper in this instance. We just want to look at Dunlin. All right. So in that case, we can create a list of species we're interested in. In this case, it's just one, which is Dunlin, and the numeric code for Dunlin is 4820. So now if we filter that species table down to just Dunlin, that should change that. And now we can see, yes, we've not got 3, we've got 1. So there it is, Dunlin, and the ID number 4820. Okay, so now that we've pulled out Dunlin, that'll help us when we go to actually download the detection data. All right. Next step, before we get to the detection data itself, we want to look at the tag deployment metadata. So we'll load the tag deployment metadata and filter it to include only the species of interest, which is Dunlin. And then we'll remove any fields we don't need and remove any tags where the deployment location metadata is missing. So if that hasn't been entered into the Motus database, maybe we see that a tag was deployed on Dunlin, but we don't know where it was deployed. So that's not particularly useful to us if we don't know where the bird was coming from. So we'll remove those data for now. Okay, so first we just need to connect to the tag depths or tag deployment table in the SQLite database. And if you want to see, since it's not stored in like a flat data frame that looks like a spreadsheet yet, like we had for the species table above, we can't just click on it and see that spreadsheet. But what we can do is get a list of the variable names that are included in that table, so we have an idea of what information is in there. So we'll do that. And this db list fields command allows us to do that. So once we run that line, it shows up down here in the bottom left in the console and tells us, okay, these are the fields that are contained in that table. It gives us our deployment ID, Motus tag ID, the project ID, the start time, end time, band number, species, etc. Okay, so that's good. But now we want to be able to actually convert it to that flat data frame table that's nice and easy to look at, see our data in there, and also exclude any tags that don't have a deployment location. So we'll run this next chunk of code, which will create a data frame called tags.meta. Okay, so now we've got tags.meta. So we've got 90 tags. And we can open that up and see their deployment IDs, their tag IDs. They all belong to project 349, which is the Fraser Dunlin project. We've got the start and end times, marker numbers, and the deployment locations, as well as the full tag ID there, which tells us it's Fraser shorebirds, etc. Great. Okay. Next up, ambiguous tags. Okay, so despite our best efforts to avoid it, sometimes there are duplicate tags transmitting in the network at the same time. And when two tags are deployed at the same time that have the same ID code, burst interval, and frequency, it can result in situations where the detections may belong to either tag, and if that happens, we have to rely on contextual information to separate them if we can. So these are called ambiguous tags, and we can find out whether there are any ambiguous tags in our data set and whether they have detection data that we'll need to examine later. So same, we connect to a new one of those tables within the relational database, which is all ambigs. And then we can turn that into a data frame so we can look at it. And so then we have a data frame called ambig here, which is 8 observations, which means we have 8 tags that could potentially, well, 4 tags within our project that could potentially be confused with 4 other tags in another project. So we'll want to keep an eye on that. And then we can check if any of these tags have ambiguous detections. And that creates another table here that tells us, yes, they do. Okay, so that's something we will want to keep an eye on going forward. And the Motus R package also has a function within it that helps us identify ambiguous tags. So, and that's called the clarify function. So we can run that and that'll show us, okay, we have our 4 tags here from the Fraser-Shorebird project, 138, 139, 140, and 141 that could be confused with tags of those same numbers from an Atlantic Canada shorebirds project. So those will be tags that we'll want to, if we're looking at them later, just make sure that we're not including detections that are actually from birds with the Atlantic Canada shorebirds project. Fortunately, there likely won't be a lot of crossover between the Atlantic Canada shorebirds and ones on the Pacific coast here, so that may allow us to separate them fairly straightforward. Okay, so now we've got our tag metadata and we've found out whether there are any ambiguous tags that we just want to keep in mind for later in case we need to examine those further. So next, we can actually get into accessing the detection data of these animals, these, in this case, shorebirds, being picked up on Motus receiver stations across the system. So we'll use that all tags view that I mentioned previously, which is a virtual view that joins all the fields from various tables within the SQLite database that we're likely to need. You can create your own views or data frames from the various tables if you want to customize depending on your needs. But for most users, the all tags view will provide what you need and is a little more convenient and straightforward than creating your own from various joins of these different tables. The all tags table can easily get quite large and take up a lot of your computer's memory if you have a lot of tags with a lot of detections. So it's often advantageous to filter out anything you know you won't need before you convert it to one of those flat data frames, the nice tables that we've been looking at, in order to save computer memory and save time. So we'll create a list of the tags we are interested in, and we'll keep only the detection data from those tags. So that will only be taking the time and memory for the tags we're actually interested in looking at. If you were going through your own Motus project's detection data, you'd likely load detection data for every tag in the project or every tag of a particular species in the project. But during this workshop, we don't necessarily have time to go through every tag individually. Remember, there were 90 tags in our metadata. That would get probably boring pretty fast to go through 90 tags. So we'll pull out a subset of 10 example tags to work with today. All right, so we can take our tag metadata table that we loaded previously, and we'll just pull out the Motus tag IDs from that table. And that will create a tag list. Okay, so yes, there were over 90 tags in that list. We don't want to look at all of them. So we're going to filter out just 10 tags of Dunlin that we're interested in looking at. So I've selected some representative tag IDs here, and that's what we'll keep. So let's take that tag metadata table and filter out just those 10 tags. All right, so now our tag list is 10 tag IDs. So that's a little more manageable. All right, so next we are going to pull out that all tags view and look at our actual detection data. So here we connect to the all tags view through the SQLite database, and then we take that all tags view, and before we convert it to that flat data frame, we're going to filter out the tags in that list of 10 tags we created, make sure that the species are Dunlin and the tags are coming from project 349, and then we're going to select the variables of interest that we want to keep. In that case, it's this list of quite a few variables that we'll end up using. I've got them listed here, and then we'll turn that into a data frame and convert the timestamps, which start out as just numeric timestamps, into a date time that's easier to interpret, day, month, year. So this is what can, if you've got a really large project, take quite a bit of time, but since we're just pulling out data for 10 tags, it should take about 10 seconds to run. Okay, so we'll give that a moment to load our data, and there we go, it has loaded. And this, I had this little system.time command up there to just tell us how long it took about 10 seconds. And now we have our table of tag detections. So that is up here in the right in our environment. And we can see that even though we only pulled out detection data for 10 tags, we've got over 500,000 hits. So that's pretty big. So you can see if you've got a lot of tags you're looking at, that could get to be a very large table very quickly. Okay, so now we've got our detection data loaded. And next we will load receiver metadata for all of those receivers that our tags were detected by. We need to rename a few fields that in that receiver table so that it's clear that they refer to receivers when we join that receiver metadata with our tag detection data. And similar to the tag metadata, we'll remove any receivers that have missing location metadata, because if we get a hit on a detection on a receiver, but the receiver has no latitude or longitude associated with it, it's not very useful to us because we don't know where the bird was detected. Okay, so we can connect to the receiver depths, the receiver deployment table in the SQLite database, and then convert that to our flat data frame that is easier for us to look at. Then we'll run some code that will rename those fields from just project ID to receiver project ID. Therefore, we know what project that receiver is associated with it, and we're not going to necessarily confuse it with the project that the tag is associated with. And we'll also remove any of those receivers that have missing location data. Okay, so we've got over 1,000 receivers in our table here, which certainly not all of those detected Dunlin, but we've still got our data cleaning yet to come. So next we can join that receiver metadata with our tag detection data. So that's in this code chunk here. We'll take both tables, join them together by their shared fields. Okay, so now our tag detection table still has the same number of tag detections, so that's good because that shouldn't change when we're just joining the receiver metadata that we want, but it now has more variables than it did before since it has some additional receiver fields. Great, so now we've got our data kind of in the shape that we want it in. We've got our detection data and we have the associated tag and receiver metadata that we need to be able to interpret it. But as I mentioned before, Motus data can be susceptible to false positive detections due to anthropogenic noise in the system, or occasionally aliasing events that make it seem like a bunch of tags appeared at one station when really they didn't necessarily, and it is simply from multiple tags overlapping signals, making it look like other tags are present. Anyway, there is, we can examine the data to remove these false positives so that we can be confident in all of the detection data being correct and real detections of animals at these locations. So now that we've done all our joins on these SQL-like database tables and created our detections data table, we can do the first small steps of the data cleaning process. So first we'll create a few date-related variables that can be useful as we proceed, and then remove any detections of tags that occur outside the time they were deployed. And this is why it's important to keep your metadata up to date, because if you deploy a tag in, say, February of 2022, but you've got a bunch of detections of it in December of 2021, those detections are not real because you hadn't deployed the tag yet. So we want to make sure any of those are excluded. So then after that, we will start working with the Motus filter. And the Motus filter, this is when Motus assigns a value of 0 to runs that are likely false positives and a value of 1 to those that are more likely to be real detections. Okay, so I'll just jump over here for a moment and mention how this Motus filter field works. So essentially, each hit in that tag detection table will have a Motus filter value of either 0 or 1 associated with it. As I mentioned, anthropogenic noise and other factors can lead to these false positive hits that are present due to the nature of radio telemetry technology. So we do have to find a way to remove them. Because these false positives are detections of signals that are mimicking real tags, the shorter the run length is, so a run length of 2 or 3 hits is more likely to be false than a long run length of, say, 10 hits in a row, because you're less likely to get noise in the environment mimicking a real tag for that long of a period. So hits with run lengths of 2, or detections with run lengths of 2 or 3 are likely have a high probability of being false positive. So the Motus filter is set at 0 for those. And run lengths of 5 or more are likely true. So those receive a Motus filter value of 1. And for run lengths of intermediate lengths, like 4, those are likely false if it's a really noisy environment, but likely true if it's a quieter environment. So the Motus filter categorizes those based on the noisiness of the site. And noisy sites are categorized as those with many runs, over 100 within an hour, and a high ratio of those runs being short ones with a length of 2. So if over 85% of those runs within that hour are run length 2, it's categorized as a noisy site, receives a Motus filter value of 0. If that's not the case, it's a quiet site, it receives a Motus filter value of 1. Okay, so back to R. So we can use this Motus filter to help us clean our data to remove these false positives. So we'll start by creating those date variables and removing the detections outside of tag deployments. And you can kind of look at your tag detection table up here in the right corner as you run this code. And you can see that a few, it did get a little bit smaller, fewer hits. So some were removed from because they were outside the deployment times. And then we'll also do some updating of the Motus filter because for sensor gnome receivers, hits where the frequency standard deviation is greater than 0.1, they're generally false positives. Then we'll remove any birds that have only detections that are likely false. So we can take those out. And then after that, we can update our tag list to see if any birds only had false positive detections and therefore were removed from our data set. In this case, that's not the case because I selected 10 tags that would be representative for us. So all of those tags have real detections. However, if you were working with a larger data set where some of these were the case, that might remove some tags. So then you could update your tag metadata to reflect that you're now including this number of tags. Okay, so this is kind of your basic processed tag detection data. And it can be helpful at this point to save a copy of your detection data. And if you want your tag metadata, now that we've downloaded it and converted it, so that way you have a saved copy if you want to come back to this analysis later. However, I'll note that the detection data is not yet cleaned to remove false positives. So we still will need to do that. But let's save a copy first so that we can come back to it later, or just so we have a saved copy so we don't necessarily have to do all these steps over again every time we come to analyze our data. So I recommend working with .rds files since they preserve formatting. But if you want to open and examine your data, you can also save a copy as a CSV file. Just be careful that some of the other, some of the fields don't get modified by Excel, especially like dates. Right, so this allows us to save a copy of the file in our project folder. So I'm going to call this file Dunlin Tag Detections. I'll also save a copy of the metadata table as well. So now I can look in there at my project folder, look at the processed data folder, and yes, we have Dunlin Tag Detections in there. Okay. Next step is where we really start looking at the detection data. So we'll do some more automated filtering to remove false positives, and then we'll make a map and signal strength plot for each bird to examine individually. That will allow us to visualize their movements and spot other detections that may be false positives that slip through the automated filters. And this can become somewhat subjective. So in order to keep it consistent and repeatable, I try to use a specific protocol. First, which we did above, we assigned a Motus filter value of 0 to all detections where the standard deviation of the frequency offset was greater than 0.1 kilohertz. And we removed all birds that only had false positive detections where the Motus filter was 0. Next, we will calculate the proportion of detections where the Motus filter is equal to 1, or likely a true detection, for each combination of tag, receiver, and day. So we'll group, we'll take each tag and look at all of its detections on one receiver in one day and look at the proportion of those detections that were likely true. And then we'll remove all of the detections where the proportion of the detections that were likely true for that bird at that receiver on a particular day is less than half, so more than half likely false positives. And this helps us to remove false detections from particularly noisy environments, Motus stations that are in particularly noisy environments that might otherwise slip through the Motus filter. At least that's what I have found. This cutoff of half you may want to adjust that to be stricter or looser, depending on what you find works best for your situation. But in this instance, I found that the proportion of half is useful. So once we've done that, then we'll create a map and a plot of the signal strength of each detection and for each bird and examine those individually. And then as we are examining those maps and signal strength plots, we can continue to identify potential false positives that got through the automated filters using the following criteria. This is the part that gets a bit more subjective. So I use the following steps that I think make biological sense, but you may have additional or different ones that make more sense for your project or the species that you're working on. So I identify and remove suspect detections that meet one or more of the following criteria. They make a large movement at an impossible flight speed. So think going from the Pacific coast to the Atlantic coast in a matter of minutes, not likely true. Or they make a large movement in the quote unquote wrong direction with no curve pattern in the detections that it is indicative of a flyby of a Motus station. So by wrong direction, that's really only useful if you're looking at large migratory movements. So I wouldn't necessarily expect a Dunlin to go from the Fraser Estuary in BC north to Alaska in December. But I might expect it to make that movement in May. And then also if there's an isolated detection, that's a detection at one Motus station far away from any other detections, and it's a relatively short run length and no clear pattern in the signal strength that indicates that it might be real, I would consider that a suspect detection. And then any detections of multiple birds at the same time at the same station that are far away from any other detections of those birds that might be indicative of an aliasing event. So say we saved our .rds file of the uncleaned detection data. If we had left R and come back to it later, then we can just load it in from our saved file. So we'll do that. And this I've called tags.detpro. You can call it whatever you want, but tag detections processed is what I went with here. And then we can look at the names of the different fields in that just to see what we've got in there. So we've got hit ID, run ID, timestamp, and lots of other informative fields that we'll use. Now, occasionally, if you deploy a tag on an animal and then recapture that animal, recover the tag, maybe the tag still has some lifespan left and you put it out on another animal, you're going to get 2 deployments of the same tag. So you want to make sure that you separate those detections and don't treat it as one if there were multiple deployments of a tag. So we can just check if there are any tags that were deployed more than once. And here we see no, false, no tags were deployed more than once. So we can work with the Motus tag ID as our unique ID, and we're good to proceed. This command here will just tell us kind of the structure of the data frame we've got and a summary of the different fields. So we can look at that just to give us some idea of the shape our data's in. Basically, this shows us, okay, we've got a table and hit ID is an integer, and then it shows us the first few numbers in that field. If we look at summary, this can be perhaps a little more useful at times to just get a sense of your data, and it could point out any glaring errors that might have been missed. So it'll tell us for each field, it'll give us the field and then the minimum value, first quartile, median, mean, third, and maximum. So if you're expecting, we can look at the timestamp field here. And if you know the dates of your project, that you want to just check, okay, these make sense. So the Dunlin project, we started it in 2020, and sure enough, our minimum date is in 2020, and our maximum date is in 2022 since it's ongoing. If I saw a date from 2015 in there, I'd be like, didn't need to check that because the project hadn't been started yet. All right, so next we can calculate that proportion of the proportion of the detections that are classified as likely true by the Motus filter for each tag at a particular receiver on a particular day. And once again, we'll get a list of the unique Motus tag IDs. We look at that here. We've got the 10 tags that we're looking at, so that's good. And then we can start filtering out anywhere the proportion of likely true detections is less than half. So we'll create a new table called tags.filt. So that's for our filtered data. All right, so we'll check our list of tags from that tags filtered table. And yeah, we still have 10 tags. So we're keeping all our tags, that's good. And next we can do some, run some code to calculate the transitions, the speed of transitions between different Motus receivers. So that will allow us to calculate the how long it took a bird to travel between 2 receivers, and that can help us identify additional false positives. And then we can check if any of it, also label them as, if they're really fast, higher than what's a biologically plausible flight speed, it'll label them as suspect, so we can check if we have any of those suspect transitions. And in this case, it looks like we don't. So that's good. We don't have any obvious, really fast, large movements to remove. And then The next step, this helps us with our mapping later. We can see potentially what might be a direct flight versus might not be based on the speed of travel. So the next step here is to start creating those maps so that we can look at each bird, look at where it went, and see if that makes biological sense. So what we're going to do to create these maps is we're going to run a loop through each of the 10 tags and create 10 plots. And we're going to save those plots in our folder, our project folder in the figures folder that I have within that. So first we use this, this function that just gets us the path of the detection, so the sequential detections. And then we'll loop through those 10 tags and create a map for each of them. So this will take a little time to create those maps, but once we get that code running, we can navigate over to our project folder, go into figures, and I've created another folder called diagnostic plots. And in case we have to go through this process multiple times, which if you have a large data set, sometimes you do, you can create a folder for each round of these checks. So I've called this round 1. You can see that it has created 10 plots there for us to examine. Okay, so now we've got our maps. The next step before we start looking at them is we want to make signal strength plots. So signal strength plots will, with each hit, there's a value of signal strength associated with that detection. So the higher the signal strength, in theory, the closer the bird is to the Motus station. There's a lot of confounding factors in the environment that can affect this, but generally, as the bird is far away from the station, the signal strength will be lower and then increase as it gets closer and closer to the station. When it's passing right by the antenna beam, the signal strength is at its highest, and then as it moves further away from the station, it decreases again. So we should, for detections where a bird is flying by a station, we can get a nice kind of curve of detection, of the detection pattern, the signal strength. So that can be helpful to look at when we're examining our detections to determine whether they are real or not. So we'll make those signal strength plots the same way. We'll loop through each of the 10 tags and create a plot. Okay, and you can see here the plots are being written to our computer. It just takes a moment to create those plots, and then now that we've got the plots, what we can do is start looking at the plots to see if they make biological sense. So I like to look at the plots side by side. So let's open up the map plot. And we'll open up the corresponding signal strength plot for the same bird. Okay. Okay, so we've got the tag ID up here. We can, and in both plots, so we can make sure, okay, we're looking at the same bird, so that's good. And then here in the little red star tells us our tag deployment location, and then the dots are the detections on Motus stations, and they're colored by the month of year that the detection happened to give us a bit of a sense of time. And then we've got on the right here, I've got signal strength plots, and each panel is a Motus receiver. And so it gives us the signal strength on the y-axis and the date on the x-axis. So here we've got a bird tagged, a dunlin tagged in the Fraser estuary in southwestern British Columbia, and then a detection in the summer over at the mouth of the St. Lawrence River in Quebec, which seems to me to be suspect. So I think that detection in the St. Lawrence is likely false. So what I tend to do to keep track of false positives that I'm identifying is I create a CSV file that I can open in Excel with a row for each tag, and then I write any notes about false positives in there. So that we can then see created a CSV file. And there it is. We have a row for each tag. We can write any notes about suspicious detections that we think are false positives in there. Okay, so we'll take a look at the next bird. Okay, so this bird was deployed here in the Fraser estuary. The tag was deployed on the bird, and it looks like it's been detected on a number of different Motus stations in the area in December and then into January. Looking over at the signal strength plot, lots of detections, lots of hits. So that all seems pretty reasonable. Same for this bird, only detection in the Fraser estuary, so that seems good. And we can see here it detected a lot at the station called Blackie Spit. Lots of detections, looks like really solid data, so that's good. All right, here's another one that seems a little questionable. Dunlin picked up over in Michigan in the Great Lakes area. So that Motus station, you can see that is a Clear Lake Motus station, and there's just one day where the bird was detected quite some time away from anywhere it was detected over on the West Coast. So if we want to take a closer look at those detections in Clear Lake over around the Great Lakes to see if whether that the pattern shows that curve that would be indicative of a real detection, we can zoom in on those detections. So we can use that tag here and just specify, or sorry, that code function here and specify we want this Motus tag ID and we want to look at the receiver detections on the receiver called Clear Lake. So then we get the plot here. That is not much of a detection curve pattern. The run length, it's not many hits, so I would say that's likely a false positive. So we would want to remove that from the data set. Okay, next one is, once again, bird is tagged in the Fraser estuary. It hangs out in there, pops down to Washington at one point, but that seems quite plausible. And so that all looks real to me. Take another look. Okay, here we've got a detection over in the Great Lakes again, likely false, but we've also got a detection up in Alaska. And that's far away from the Fraser estuary, but much more likely that Dunlin would be migrating to Alaska in the spring than over to the Great Lakes. So that seems like it could be real, but if we want to take a closer look just to make sure it seems like that the signal strength indicates that it's a real detection, we can zoom in on that Alaska detection. And here you see it does have that nice curve pattern to it and lots of hits. So that suggests to us that that is a real detection and that bird did migrate up to Alaska. Similarly here, we've just got a one detection over in the Great Lakes area. Seems false, so we'll remove that. And once again, we've got another Alaska detection, but that's along the Dunlin migration route. And we know that the station there near Cordova is a major shorebird spot. So that one, again, seems real. And we've got another detection on many stations within the Fraser. So that all looks good. Lots of data there, so that's great. And similarly here, lots of detections around the Fraser and the Salish Sea. Likely all real. And that's our 10 tags. So we identified that there were problematic detections at 4 receivers in the Great Lakes St. Lawrence region. So we can filter out any false positive detections at those receivers. We'll keep all the real detections of those birds on the West Coast, but we'll just remove the ones of them in the Great Lakes area. So what we'll do is remove any detections at those receivers, creating our new table called tags filtered to. And then now that we have cleaned those data, we've removed any last false positives that seem to be in there. We've got our processed and cleaned tag detection data ready to go for your Motus analysis. And from there, you can take your tag detection data and run whatever your analysis plans are for your data. So we can save a copy of that detection data like we did before, but now we're saving a copy of the cleaned detection data. So I'm going to call it Dunlin tag detections clean. And then once you want to start doing your analysis, you can just load in that already cleaned, ready to go data set. So that was a whirlwind tour of downloading, processing, and cleaning Motus data. We covered a lot of ground, so I hope the presentation materials are helpful when you go back to analyze your own Motus data. Ariel Linsky helped develop a lot of the workflow I use and presented today. And of course, many members of the Motus team over the years have been instrumental in working on the database and the R package. Thanks for your time today, and I'm happy to answer any questions.